spotkanie jest dedykowane kompatybilności technologicznej z racji tego, że jestem przewodniczącym polskiego oddziału, także mam możliwość, z tej możliwości korzystam, zapraszać różnego rodzaju dystyngowanych wykładowców. Dzisiaj przyjechał na spotkanie Mathias Magdowski z Magdeburga. Mathias, come to us. Yes, I would like to introduce you Mathias Magdowski.
I'm a scientific co-worker and lecturer at the Otto von Guericke University of Magdeburg in Germany. I will tell you in a moment where Magdeburg is located. As you can see, I'm working for some Institute for Medical Engineering, and even if I don't have to do too much with medical engineering, but I work for a chair for electromagnetic compatibility, and I think this is also the reason why most of you are here today. About the IEEE EMC Society that Krzysztof also already introduced a little bit. So we have a website, you can see the link here on top, the EMCSociety.org. And you can find all information there, what we do, what we are. Maybe most interesting for you and what I've already talked about, this EMC Society is organized in different local chapters. So if you click here on chapters, then we can check for chapters and chairs. And now a map should open up. And if we zoom in into Europe and zoom in into Poland, and wait for some time because my internet connection here obviously is not the fastest and the map needs some time to load, then something should pop up here. And this is our local chapter in Germany, but this is the local chapter in Poland. If I click on this here, right here in Poznan, where we are located right now. And you see the contact of Krzysztof. And so IEEE organizes lots of technical activities like this distinguished lecturer talk here. And if you like this, if you like something like those, we are always looking for active volunteers who also are active organizing stuff within the IEEE EMC Society and within the local chapter, so please be invited to help us with our work if you like this. Title of my talk today, as already announced, Robust, Precise, Fast, choose 2 for radiated EMC measurements. Before diving into the topic, I would once again try to introduce myself a little bit. I was born in 1984, like the book. So you can calculate yourself how old I am. In this year, it's especially easy to do so. I live in Magdeburg. I will show you in a minute where this is located within Germany. I'm married. I have 2 children, and I have a background in electric engineering. So I studied electric engineering more than 20 years ago at my university there in Magdeburg. Since 16 years, I worked there as a scientific co-worker, researching and lecturing. I also did my PhD there about, as you can read, comparison of stochastic and deterministic field coupling to transmission lines. So something like this that I will talk also about today. Immunity measurements in anechoic chambers and reverberation chambers, but today I will talk more about the emission, not about the immunity. And since 2015, I'm also active as a flying faculty lecturer, giving not only talks like this one for the IEEE EMC Society, but also lectures for students. I've been to Israel, I've been to France. In former times, I've also frequently traveled to Russia, which of course doesn't work anymore. So I have lots of experience in this. This is the building of our faculty. This is also where some of our laboratories and where my office is located. And this is another picture of our city. So we also have a river, like here in Poznan. Our river is called Elbe. We also have lots of churches and a large cathedral. And it's also quite a nice place, so you're invited to visit Magdeburg. It's nice to walk. So we don't have this big historic old town because large parts of the city have been destroyed during the Second World War, but it's of course nice to walk along the river there and visit the cathedral, visit some museums. And if you wonder where Magdeburg is located, so it's west of Berlin, about 1.5 hours by train or by car, somewhere in this triangle between Berlin, Hanover, and Dresden that most of you might know because these are more the touristic destinations within Germany. So we are in the central eastern part of Germany, let's say. And what Magdeburg is also famous for, and who was the name patron of our university, Otto von Guericke. It's a picture of him. He was also a scientist and a researcher, also an engineer. He was also mayor of the city for some time. And he did, he also kind of invested ESD. So yesterday when we visited the laboratories, there's also some test bench here for electrostatic discharge. He also kind of invented this because he had a large sphere made out of sulfur that you could rotate, and then due to triboelectricity you could separate charges and make tests with these charges. But what he's more famous for is the Magdeburg hemispheres, an experiment that is displayed here. So he also experimented with vacuum, and he invented the air pump. So he took two large hemispheres, about 60 centimeters in diameter, and put them together just with a seal, and then sucked the air out of it, so that within these hemispheres there was nothing or very, very low air pressure, very good vacuum. So these hemispheres were pushed together by the force of the external air, by the external air pressure. And to demonstrate, to show how large and how powerful this force is, he did a famous experiment with 8, you can see it here, with 8 horses on one side and 8 horses on the other side. And these 16 horses in total were not able to pull the spheres apart because the force of the external air is so high, so large. And then the legend says that a small boy child came, opened up the valve, and the air would flow back into the hemispheres, and then the hemispheres would just fall apart because this force was now, the external force was now missing. So he maybe also kind of invented science communication to people. And we, from time to time, it's of course, with the horses, sometimes it's kind of challenging and difficult, but for anniversaries of the university, we sometimes repeat this experiment. So last year, our university celebrated its 30th anniversary, and there we also did this experiment. I think just with 12 horses and not with 16, but it's still kind of impressive. So you might know the picture with the horses trying to pull something apart, also from a big jeans manufacturer. So same experiment but different force, of course. Yeah, but I think Levi Strauss he has stolen this idea from. Okay, so just some organizational matters. If you would like to have a copy of the slides, no problem. I will share them to Krzysztof, and he can distribute them. You can also send me an email, no problem. There might be a recording, so I'm doing a recording on my computer here. Hopefully it works. You never know. There will be a recording by Tom. So we will see, maybe. And if you have questions in between, with pleasure. Don't wait till the end. I think we still have lots of time towards the end for Q&A, but if you have questions in between, don't hesitate to ask the question. Even if I'm speaking very fast and without period and comma, just raise your arm, just interrupt me. Don't wait till the end with questions. Don't wait until you probably have forgotten about the question. Okay, so then let's dive into the topic. I'm not sure if everyone is really from the field of EMC, so motivation is for sure that we have and we all use lots of electronic devices all the time, and these devices on purpose or unintentionally can create electromagnetic fields and will create electromagnetic fields, and then these fields propagate and can couple into other devices, and this can create some disturbances. And every cable that you have everywhere will also act as an antenna. It will radiate fields, it will pick up fields. And so we might have sources of disturbances like this Wi-Fi router here. They could create and will create electromagnetic fields, and then they could create some disturbances, for example, in a TV set, something like this. And so we want to ensure that such interference, such incompatibility not happens. So we want to ensure that there is electromagnetic compatibility between these devices. And the question that everyone asks is, will there be some interference or not? Will there be sufficient immunity of devices, and will there be only low emissions? And today I will somehow focus on the emission side and, as said, compare different test environments with each other. And then the second thing is that many engineers working at laboratories, that sometimes, unfortunately, they just apply standards and don't think about the underlying physics. So what really happens there? How does the field look like? What are properties of this test environment? And they just say, okay, push the device and test in there. We have some software. We push a button, run some automated measurement, and don't really think about what happens there, and just apply the standards. So just applying standards is, of course, easy. It's more challenging to understand and to think about the underlying physics. But this is what I would like to encourage you today a little bit to do so. So I invite you to don't be that kind of test engineer that just applies these standards. So this already brings us to some kind of fundamental question. So if we want to somehow measure and analyze and evaluate the electromagnetic emissions of some device in a test, and the question is, what is a good measurement to do so? And what you measure in anechoic chambers and semi-anechoic chambers is field strength measured in volts per meter, or you can also express it in a level, in dB microvolts per meter, something like this, in a certain distance. So the measurement facility here at Łukasiewicz is a 3-meter chamber. You would do measurements in 3-meter distance. And typically you want to do the measurement under far field conditions. So you can start to do measurements there, let's say from around 100 megahertz. Then another idea would be not to measure field strengths, because here this would be electrical field strengths, and in the far field there's a fixed ratio. But if you go to near field, there might be higher magnetic field than electric field and vice versa. So what would be also interesting is to measure power flux density in watts per square meter, also at a certain distance, because the farther you go away from a device or a test, the smaller the signal, the smaller the amplitude will be. And the other idea, and this is what we do in reverb chambers, is to measure total radiated power. So what is radiated over all the directions of some equipment under test. And the next question is, in which environment will we do this measurement? Is it really a reflection-free environment that we try to replicate or reproduce in a semi-anechoic chamber where there are no reflections at all? Because if you look in a typical environment, maybe like this office room here or meeting room here, at least this wall and maybe the outer wall, I think this is a dry wall, and this I'm not sure, but there will be lots of walls made out of steel reinforced concrete. So there will be reflections from steel walls, there will be reflections from the ceiling construction and so on. So in real life, you don't have this perfect reflection-free environment. There will be some reflections from the surrounding. And then if you go to industrial places with lots of metal around, if you are located in a train, in an aircraft, in a car, in a big ship, then there will be lots of metal around. So you have an environment with lots of reflections. And then the question is this field strength in a certain distance measured in an anechoic environment, is this really a good measurement to measure practical EMC emissions and disturbances? So these are really the fundamental questions I think everyone should think about a little bit, and that I'm trying a little bit to discuss today. So structure overview is, I will briefly talk about measurements, what is done here at Łukasiewicz, measurements in semi-anechoic chambers and anechoic chambers. Then I will talk about measurements in reverb chambers, what we do more in Magdeburg, or what we do also measurements in semi-anechoic chambers, but me, myself, doing lots of measurements in reverb chambers. Then the question is how to convert or how to correlate these results. And as discussed in the interview before, it's a little bit like comparing apples and oranges with each other, because it's there's kind of a fundamental difference between these two environments, but at the end, both should taste good. Both should give you a kind of similar answer. And then to prove this a little bit, I can show you some measurements that we did with some generic EUT in our semi-anechoic chamber and our reverb, and at the end, of course, there will be a summary. Okay, so let's start with semi-anechoic chambers. So first thing is, if you want to measure emissions, you want to measure emissions just of your device on a test. And if you measure immunity, you also want to potentially only disturb your device on test, and you will not want to disturb half of the city around you. And for emission, you don't want to measure all the Wi-Fi stations and all cell phone base stations and radio stations and so on. So first thing is you need to shield yourself from the environment. So shielding works with metal walls. So you take a metal room, use walls for metal for the walls, for the ceiling, for the floor, and these metallic walls act for the electromagnetic waves like a mirror. So everything that comes from the outside will be mirrored back, but everything that you create in terms of emissions on the inside would be also mirrored back by the walls. So imagine you are in a room where there are mirrors everywhere, and you switch on a flashlight. So what will happen? It's getting bright. Yeah? You will see lots of reflections, because light will be reflected and re-reflected and re-reflected, and you don't know where the light is coming from and then where the light is going to, because you will see lots of reflections of this single beam of light from a flashlight or from a torch. And the same would happen with the electromagnetic fields inside such a shielded room. And this is also what happens in a reverb chamber, but there we somehow deal with it. But in the anechoic chamber, you don't want to have this. So you need to do something so that the walls are not reflecting anymore. If you think back to the analogon of this room with lots of mirrors, what you could do is, like in the Rolling Stones song, paint it black. Yeah, you could take some black paint and paint the mirrors black, and then the mirrors won't reflect anymore, because the black paint on the surface is somehow absorbing the light waves. And light is also just an electromagnetic wave, but does anyone know what is the wavelength of visible light? In hundreds of nanometers range, so somewhere between, let's say, 400 and 700 nanometers. Very tiny, very small, and that's why the tiny surface roughness of this black paint is sufficient that if there's some ray of light coming, so the surface of the mirror is very flat, so you get a reflection with the very same angle, and the black paint has a very rough surface, so if some ray of light is getting in there, it will be reflected and re-reflected, and if it may exit, it will not exit with the very same angle. And so our electromagnetic waves, they have much lower frequency and much larger wavelengths, so we need something like black paint, something like a rough surface in the order of magnitude of the wavelengths. And I mean, these are these absorbers that you have then all on the walls. They act like black paint for light. And then usually there's a turntable. You put your device on a test on the turntable, let it radiate, and it will radiate in all directions. But all directions will be absorbed, and just the direction that more or less directly goes to the receiving antenna, this is what you measure. And you know the distance, and then you can rotate the device on test on the turntable and measure the emissions in terms of field strength in a certain distance as a function of the rotating angle. And so you might already see some kind of advantage and disadvantage here. So the advantage is we can say what the device on test will radiate into a certain direction, but if it, for example, radiates exactly to the top or radiates to the bottom, you will not measure it, because it will just go into the absorbers. And so you could do the measurement also in a fully anechoic room, then you would just measure the direct path, and in a semi-anechoic environment, the floor is reflecting. The floor is made out of metal, so you do not have just a direct path, you also have one reflection at the ground, and then you do a height scan with the antenna to capture the positive interference between the direct path and the path with one reflection that has slightly more length, and then there will be a phase shift and can be positive and negative interference between the two waves. And that's why you do a height scan with this antenna. And this is how this looks like in practice. So this is a picture of our large semi-anechoic chamber that we have in Magdeburg with 10-meter measurement distance. This is an older picture. If you look at recent pictures, then this is the back wall. Then these absorbers at the back wall are a little shorter because we built in another large door there so that we can easier move larger cars, vehicles in and out. Okay, so what you would really like to measure there in a perfect world is radiated field strength in the far field, and you would like to get the maximum over all directions and for all frequencies of interest. And in practice, what you actually measure is radiated field strength in a certain distance. So at low frequencies, it must not necessarily be far field, but if you are these 3 meters, 10 meters away, in most cases it's okay. And then you do not really get the maximum over all these directions because you cannot measure all directions. You typically just do certain steps with the turntable. Maybe 90 degree, maybe 30 degree, maybe less, but then it's consuming more and more and more time to do so. So you cannot really get this maximum. And you cannot also measure all frequencies. You have a certain frequency sampling. And as already mentioned, if your device on a test radiates to the top or radiates to the bottom, then you neglect this. You will not measure it. It will not get to your antenna. A simple idea of a reverb chamber is, once again, if we want to do emission or immunity measurements, we need to shield ourselves from the environment. So once again, we take a shielded room. And as already mentioned, this shielded room brings this problem that we also get lots of reflections and echo of these electromagnetic waves inside the room. And that's why it's called also a reverberation chamber, because you have this reverberant environment with lots of echoes of the same field. So we get lots of waves traveling back and forth in different directions within this room, and they will superpose with each other. And then once again, there can be positive interference, so where the different waves traveling in different directions will add up and will reach a high field strength. And because these standing waves in electromagnetic field theory are called modes, and this is the device that we use to change the modes, to steer the modes. This is called a mode stirrer. And then the whole thing is sometimes also called a mode stirred chamber, because it's a chamber where you stir the modes. But more common now is this is the name reverberation chamber. And this is how this looks in practice. This is a picture of our large reverb chamber that we operate in Magdeburg. To be honest, this motorcycle which is on the picture was never actually tested for EMC. It was just placed in the photograph to make the picture look nice. It was a motorcycle of a former colleague in Magdeburg. But this made the photo kind of popular. So if you check the English Wikipedia for electromagnetic reverberation chamber, you will also find the photograph there. And so here you can see the stirrer. This is also the old, so this picture is probably 20 years old. So this is the old stirrer, but you can see the different metal plates. And if you rotate this, you change the reflection of the waves, change this wave pattern inside there. You can also see some field probes to measure fields. In the back, you can see some logarithmic periodic dipole antenna to create a field. So these are the antennas that we use up to 1 gigahertz, and then above 1 gigahertz we use these smaller yellowish horn antennas here. You can also see a camera, a shield camera, to look inside the chamber, also from the outside, monitor the device under test. So this is how such a practical chamber looks like. The chamber that we have in Magdeburg is about 4 by 6 by 8 meters. So it's, let's say, half of the size of this room here. And so about 200 cubic meters of volume. And the first cavity resonance there is at around 30 megahertz. And with the new stirrer, we can operate and use this this environment, this facility, let's say, starting at around 150 megahertz. But one disadvantage of this reverberation chambers for sure is that they have a very strict low frequency limit. So if you would like to build a reverberation chamber that would already work at, let's say, 30 megahertz, then it would be really, really huge. And even building a chamber starting to work, let's say, at 80 megahertz, at 100 megahertz, then you probably need to have a chamber the size of this room with a very, very large stirrer, and you need to have a very powerful motor to operate this and drive this. So then something to give you something to think about, and there will be a second survey in a moment, is that some years ago, some person asked me at the German EMC conference, EMV in Düsseldorf at this time, hey, you do measurements in this reverberation chambers, I have a question for you. So if you do measurements and if you had hit a resonance of this resonator, didn't you get then an incredibly high field strength? If we operate such a reverb chamber correctly, we always hit the resonance of the chamber, and we always not hit just one resonance of the chamber. We will hit 2 or 3 or 4 or even 10 of these resonances at the very same time, and we need to have this for proper operation. Because otherwise, if you have just one main resonance of the chamber, you can rotate the stirrer and do something there, and nothing will really change. Okay, so thanks for participating. So then the question is, okay, what can we do to steer the field? As already mentioned, we can have this mechanical stirrer that is rotating. You could also have a chamber where the wall is moving. I will show you a picture of this in a second. What also works is that you change the position of the antenna. But then once again, you have cables attached to the antenna. It's somehow difficult. You need to have a good mechanical construction to relocate the antenna without messing up the cables. Or you could electronically switch between different antennas, or have different antennas and then have signals with different phase shifts between the antennas, which also can be done very fast. So every mechanical movement always takes time because you have this mechanical inertia. If you do electronic switching, it's very fast, but the disadvantage of the several antenna approach is that every antenna also introduces losses inside such a chamber, and you typically want to have a quite high quality factor, at least for immunity measurements, because this is one main advantage of such reverb chambers. If I go back some pictures here. So if you do immunity testing, you only need very, very moderate input power to reach a high field strength inside the chamber because of these resonances, because you somehow reuse the field. If you do an immunity testing or immunity test in an anechoic chamber, you take a very expensive and very powerful broadband amplifier, generate your signal, radiate it with some antenna, then it will hit your device test once, just once, and then it will go into the absorbers and will be converted, will turn into very expensive heat. And the idea of a reverb chamber is, okay, you take your power amplifier, you generate a signal, you transmit it with the antenna, you hit your device test, but then it's reflected and you hit it once again, and it's reflected, you hit it once again. So you can reach much higher field strengths in a reverb chamber than in a semi-anechoic chamber. And so for this immunity testing, you could also just do very narrow band changes of the frequency. So if you, for example, change the frequency from 200 megahertz to 201 megahertz to 202 megahertz and so on, there should be drastic changes of the field within the reverb chamber, but you would not expect a completely different behavior of your equipment under test, because your equipment under test, if you do immunity testing, you do not expect it to have a super high quality factor. So the bandwidth, the resonant bandwidth there will be rather large in terms of 10, 50, 100 megahertz. But due to the high quality factor, the bandwidth, the modal bandwidth of the reverb chamber will be very, very small. But this only works obviously for immunity testing, because for emission testing you cannot control the emitted frequencies by your device under test. And yeah, the switching between several antennas, what causes losses inside the chamber, you have losses at the walls. This will be dominant at the high frequencies. And at low frequencies you have losses within the antennas, because every transmitting antenna also acts as a receiving antenna at the same time. And at low frequencies and large wavelengths, the antennas have a large effective area. So they suck a lot out of the field, out of this chamber once again. So another nice idea is mentioned is to have movable walls. So what works very, very nice, and we have also done lots of experience in recent time in Magdeburg, as you might seen if you look at my LinkedIn account. There are some videos and photos of this. To do reverb measurements in shielded or in tents made out of shielding textile, metallized textile. And then you just shake this tent, or you just move the walls of this tent. You can also place a stirrer inside there, but what is much more effective in changing these boundary conditions of the resonator is just shaking the tent and moving the walls of this tent. And this is an idea that was made popular by my colleague Frank Levering from University of Twente in the Netherlands, and he's also working for Thales. And Thales is a large company that does lots of stuff. I know them because they build these cashier devices in supermarkets. So sometimes they are made by Thales, but Thales also develops radar systems, for example, for ships. And if you want to test the radar system of a ship is very huge. You cannot place the ship inside your laboratory. So once again, you have the same problem. If the ship cannot go to the laboratory, your laboratory needs to go to the ship. And that's why they made this in situ testing on ships with these mobile reverb chambers. And behind there would be something like this radar antenna on a ship. And so this is some demo, and what you can see there inside is neon tubes, and the field strength is so high that these neon tubes are starting to glow, and here you can also a little bit see the field pattern, the field that is usually not visible, so that there is higher and smaller field strengths and higher and smaller field strengths at different positions inside the room. And this is some chamber. I think there's one at Eindhoven, also in the Netherlands, and this is a picture from Chinese University at Nanjing, and they have made a wall stirrer, and if it's operating, it little bit looks like something breathing in and breathing out and breathing in and breathing out. At the end, I would say it's a nice academic experiment. It's not much more practical than just having a rotating stirrer. It maybe consumes slightly less space, but it's a very elaborate mechanical construction, and at the end you cannot move it really fast. And if you have a rotating stirrer, you can move it much faster if you like. And so nowadays there are very fast sensing field probes, and if you change your field fast, if you measure the field fast, you can save lots of measurement time. This is one advantage of reverb measurements, being fast, but this mechanical construction unfortunately is not very fast. Okay, so then a short look on the statistical properties of the field. What you want to have at the end is a homogeneous field. Your field should not depend, at least on a statistical basis should not depend on position. So for one fixed boundary condition, for one stirrer position, the field will be strongly inhomogeneous because you have this maxima and minima and nodes and antinodes of the field. But if you rotate the stirrer and measure for different boundary conditions or for different positions of the stirrer, on average you should get the same field strength everywhere, except if you go too close to the walls, because your walls are made out of metal and the metallic walls will short circuit the tangential component of the electric field and also the normal component of the magnetic field. So if you go close to the wall, field strength there will be smaller. Or at least the tangential one. I mean, the power of the field will then somehow go into the normal component of the electric field and tangential component of the magnetic field. But the advantage is, it does not matter where you place your device on a test in the reverb chamber. As long as if it's far away or far enough away from the walls and from the stirrer and from the antennas. But then you can freely place it. And the second important property is you want to have some isotropic field, and isotropy means field is independent of direction. Once again, for one stirrer position this will not be the case, but on average, for many stirrer positions you will get a nicely isotropic field. And this means it does not matter how to orient your equipment under test. And okay, orienting the equipment under test is maybe not such an issue, but this also means it does not matter how you orient your cables. So if you test the laptop, for example like this one, you will for sure always place it like this. But then in an anechoic chamber or in a semi-anechoic chamber, the result, the emission measurement result will strongly, if you have some experience you will agree, will strongly depend on will the cable will go into this direction and then will go to the ground, will the cable go in this direction and will go to the ground, will the cable go in this direction and then will go upwards. And you might get completely different results depending on how you place the cables in such an environment. Why? That's why most of the standards strictly define where and how to place cables and for which distance and how the cables should be terminated and where they will go to ground and so on. So typically you don't have this issue in the reverb chamber. You just place the cables somewhere and you don't care. And then it depends on, it somehow depends on the cable, but it's more depends on how long are your cables, what are intrinsic resonances of the cable, or how is the cable terminated at the end. And as said, these statistical properties are only valid within the working volume. And the standard mentions that you should observe a minimum distance to the walls of a quarter of the wavelengths. I would always suggest to have something larger, maybe half of the wavelengths, but something in this range. Dziękuję. So at the end, what we operate as a reverberation chamber for EMC purposes, every one of you has something like this at home. You call it microwave oven. You use it to cook chicken. We use it to cook electronic chicken, test devices for immunity, but a microwave oven at home is very similar. You have a magnetron that creates electromagnetic waves. You have this shielded cavity, and then you also have these minima and maxima of the field. What makes that if you put some food in there, the food would get hot very quickly and burn in some places, and in other places it might stay cold. And so what the microwave oven manufacturer does, it builds in this turntable so that moves your food through the field so that the food gets evenly hot. So if people don't really know what happens inside the microwave oven, they just put the food on the center of the turntable so that it rotates, but it does not really change the position. So it won't work as well as if you put the food, let's say, on the outside of this turntable, that it really nicely moves through different field positions. So if you want to get your food evenly hot, put it on the outside of this table, that it nicely moves through space. I mean, by the way, you can also use your microwave oven at home to measure the velocity of light, if you like. So for this, you need a larger piece of chocolate. Of course, you remove the aluminum foil and you put the chocolate inside the microwave oven, and you need to somehow block or disable this turntable, or you need to put it in a higher, somewhere above, but it should not move, it should not rotate. And so what will happen is that the chocolate will burn at some places, and in other places it will stay cold. So then you take a ruler and you measure the distance between 2 or 3 hotspots, and from one hotspot to the next, you have a full wavelength of the field. And so if you measure this with a ruler, you should get something like 12 centimeters, which is the wavelength of the field at 2.4 gigahertz. And 2.4 gigahertz is the frequency that the microwave ovens operate. It's such an ISM band, industrial, scientific, medical, that is also used for Wi-Fi, and it is also used for Bluetooth. Why sometimes Bluetooth headsets fail if you operate them close to a running microwave oven. And so from frequency and wavelengths, if you just multiply them with each other, you get the velocity of light. And so if you do this 12 centimeters or 0.12 meters multiplied with 2.4 gigahertz, and this gives you the 1/2, then you end up nicely with something like 300,000 kilometers per second, which is velocity of light. So it's possible to measure this with household equipment with a microwave oven. Say again?
It's most important. The bar of chocolate is the most important.
And the bar of chocolate, of course. This is you need a bar of chocolate. Without this, it won't work. You can maybe also try cheese or something like this, but something where you can later on nicely see these hotspots of the field. Okay, so in reverb chambers, what we would like to measure is total radiated power for all frequencies, because if something radiates, it will radiate wherever it likes, but no matter in which direction it will radiate, it will be always reflected by the walls, and at some time it will end up at our receiving antenna. So no matter in which direction your device and test radiate, you will always measure it with your receiving antenna. And what we actually measure is total radiated power for each sampled frequency, but there is some remaining statistical uncertainty of the field, and this is also mainly due to we have some remaining inhomogeneity and anisotropy of the field, and we also not measure all stereo positions. We just measure certain stereo positions. We have a limited sample size of our statistical ensemble. So this somehow, let's say, a little bit falsifies the result. But the big problem is why people don't really use this. There are no limits for this. So all the limits given in the standards are for electric field strengths in a certain distance, and there are no or almost no total radiated power measurements. So this is really some big problem and some big issue. Okay, so then we can discuss how to convert the results. And to do this, we need to define something first, which is called electrical size of some equipment under test. So let's assume we have some equipment under test, once again, like the computer here, like the laptop. And then we put a virtual sphere around this, and we measure the radius of the sphere. This is what we call A. And then from our frequency of interest and the wavelengths, we can also calculate a wave number. And wave number has the unit 1/meter, the radius has the unit meter, so these units will cancel each other, so this K times A is some unitless, some dimensionless quantity, and this is what we call electrical size of an object. And okay, there are some questions remaining, so what really belongs to my equipment? Is it just the computer, just the laptop here? Does the cable also belong to it? Do I need to take this cable into account when measuring the radius? And to which extent do I need to use the cable? But let's say we we somehow know how to deal with it. We have some size of our object. And now we can distinguish two cases. And the first case is this k times a is smaller or considerably smaller than 1. And in this case, radiation pattern looks like a donut. Unfortunately, today at the buffet, we don't have any donut. I should have brought a donut from a bakery, but everyone knows a donut. And so the radiation pattern of every electrical small EUT, no matter how complex it will be, will more or less look like a donut. Sometimes the donut will have a kind of a strange shape. It will be a little asymmetric, but everything looks like a donut. And to measure the maximum emission of this donut, it's really sufficient if you would measure from in 90-degree direction. So if you measure from this direction, from the back, from this side, and from here, you would measure the same in every case. And even if we would like sample in this sphere here, so from the top you would measure nothing, but from here we would measure the maximum. From here we would measure the maximum. From the bottom we would measure nothing. So from this donut, it's fairly easy to get the maximum dimension, the maximum emission of this radiation pattern. So now for electrically large EUTs, and for this I need to find a video on my computer quickly. So for electrically large EUTs, it's looking more difficult and more different. Let me go to full screen. So this is some video that Magnus Höjer from Swedish Defense Research Organization has created, I think also something like 15 years ago, 20 years ago. And it's really based on measurement. It's not a simulation, it's based on measurement. And they have taken a rather large object, something like a cabinet size, and measured the emission for different frequencies. And so here you can see the frequencies running up. Here you can see something like the maximum level that they got. And this plot here is always normalized to the maximum. And it's one spherical cut of radiation. And you can see that, for example, in this case, if we would measure at 90-degree angles, so here, 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 and here, we would not really get maximum emission. The maximum emission moves around. And it's very difficult to predict where your maximum emission will be. And sometimes it's here and sometimes it's there and so on and so on. And even if you measure in finer steps of the turntable, maybe 30-degree, maybe 10-degree, still you have just a limited chance to capture the maximum emission. And the thing is, if you go higher and higher and higher in frequency, or if the electrical size of the object gets size in comparison with the wavelengths, gets larger and larger and larger, then this radiation pattern gets more and more complex, and these lobes of radiation get thinner and smaller and narrower, and it will be more challenging and more challenging to capture the maximum emission. And this is a problem that everyone has when doing measurements with large objects at high frequencies in semi-anechoic chambers. And so it's really, really challenging then to capture the maximum emissions. Okay, so let's stop the video. I can maybe fast forward to I think the video ends at something like 20 gigahertz or 18 gigahertz. So you can see that it's looking like a hedgehog. Yeah? So you have very, very many of these radiation lobes, and they are very, very, very thin. In the semi-anechoic chamber is more smooth over frequency. And so the results have been converted assuming a directivity, a wrong directivity of just 1. So the difference between the two curves is really, let's say, the remaining directivity, the through directivity of the equipment under test. But you can see that in general, these curves from their behavior or frequency agree quite well. And let's say these ups and downs, the resonances that you see are resonances of the equipment under self-test, of the equipment under test itself, of the transmission line antennas and loops antennas on the surface. And so then what he also did, he did lots of other stuff, but what I selected for this talk is he repeated the measurements for different step sizes of the turntable in the semi-anechoic chamber. So if you measure just with 90-degree steps, you get this green curve. And then if you repeat the measurement with finer steps of the turntable, going down to...
Max hold.
Exactly, and I think this is some kind of max hold. And so if you measure more directions, if you sample more points of this radiation pattern, then you also get a higher maximum field strength. And probably if you would go down to even smaller steps, like 5 degree, 2 degree, 1 degree, then this curve would, especially at the high frequencies, once again might go up a little bit. And so this here, and you can see that the difference sometimes can be up to 5 dB, something like this also here at the end. So if you have large objects, if you go to higher frequencies, the sampling in 90-degree steps is very probably not sufficient to capture maximum emissions inside a semi-anechoic chamber radiating emission measurement. Okay, so to summarize, what you would like to do for robust EMC measurement in a semi-anechoic chamber, or what you would do in a semi-anechoic chamber is to do also these kind of robust measurements, but what is holding you back is the EUT directivity. You don't know this. Yeah? I cannot stress this enough. And you cannot assume this donut-shaped radiation pattern of a dipole also for higher frequencies. It will not be the case as you've seen in the video. So what you could do is you could go to a reverb chamber, do measurements there, also at high frequencies and small wavelengths, and it will independent of position, polarization, and so on, because you have this isotropic homogeneous field. It will also not depend on directivity of your EUT, but you measure total radiated power and there are no limits for this. So you get a nice result, but you cannot directly apply it for some standardized measurement because there's no limit for this. So everything good is never together. Yeah, so the coming back to the title of the talk, what you would like to have is you want to have a robust measurement, which means does not matter exactly where to place the device on test. It does not matter how exactly to place and orient cables. You just put it in there and somehow measure. You want to have it fast within a reasonable time, and you want to have it precise, so it should be repeatable and it should be easy to replicate and so on. So if we try to combine this robust and fast, then we do measurements in reverb chambers. For sure, it goes quite quick and we have this robust environment, but it's not precise in terms that at the end, okay, we only know our equipment under test has a problem at this certain frequency. There will be a high emission at this frequency, but still we don't know in which direction will it radiate, and we have no clue. Looking at the device, what is in this direction? Is it some hole in the shielding? Is there some aperture? Is there some display? You have no information how to debug the device from this type of measurement. So we could also try to do a robust and precise measurement going into a semi-anechoic chamber and doing full sampling, really measuring very, very fine steps of the turntable. Then you get the perfect full picture at each and every frequency. How will the radiation pattern of your device on test look like? What will be the maximum emission? And in which direction will it radiate, so you can have some information for debugging and saying, okay, I need to change something at my device, at my prototype, to lower the emission into this certain direction. But this will take a very, very long time. So for sure, it's not fast. And then, of course, you can go to you can do the same, but you can undersample and just measure 90 degrees or just measure 30 degrees, something like this, or just concentrate on certain frequencies. So it will be precise and fast, but then it will not be robust, because you have to have some a priori knowledge about your radiator, which frequencies are of interest, how will the radiation pattern look like, something like this. So the perfect test environment, which is somewhere in the center of this Venn diagram, unfortunately does not exist yet. Okay, so this concludes my talk. Thanks for your attention. And once again, I would be happy to answer some more questions. And before doing so, I think we can also have a short snack.